Uh, okay. I think it's working. Um, Hello. Yeah, I am. I don't know. How do I start an intro? Well, let's see. Self-introductory. Okay. Hello, everyone. Hello, friends. Today I will be attempting to teach about elasticity. Why elasticity, you might ask? Because I have an exam tomorrow, and as I don't know, maybe Feynman. I forgot to set it. But yeah, basically someone said the best way of learning is to teach others. And I hope that's true. Yeah, I think I'll be uploading this video to YouTube, maybe to share it to my friends so they can also learn. So yeah, thank you. Anyway, oh, by the way, I'm writing on mouse and it'll be kind of slow. Let's begin. Elasticity. So you might be asking, what the hell is elasticity? Well, elasticity is basically this. Something, let's say this thing, if given a force, will change its shape or get longer. As you can see, there's an extension here. This is new. Wow. But when the force is removed, it will go back to its original shape. There's no more force here. As you can see, it's the same. So basically, something given a force, it will get longer or maybe shorter, and if the force gets removed, it goes back to its original shape. Okay. Now, in this elasticity, I will be talking about a few things. Maybe I should have prepared in advance. Hold on, let me. Oh, okay. First is stress. Second is strain. Third is the Young modulus. Oh goodness, my handwriting is horrible. Sorry. The Young modulus. And then we'll be looking into Hooke's law. So therefore there will be a lot of springs here. Hooke's law. And there'll be also some energy too. More specifically, something new is the potential energy of springs. Oh, and also spring formations. I don't know the official naming of this, but I'm calling it spring formations. Spring formations. And surprisingly, spring formations are pretty similar to electricity stuff for formations. Yeah, just a fun fact to you guys. Okay. Yeah, these are the things we'll be talking about in this quote-unquote video. Let us begin one with stress. Stress. Basically, when you give an object a force, it is experiencing stress. The way we calculate the stress, or I think the symbol is sigma. That's sigma. F divided by A. F being the force applied to the object, and A being the cross-sectional area. Cross-sectional area. You might be wondering, what the hell is a cross-sectional area? Well, for example, let's say we have a wire. This is a wire. And if you cut it, we'll see that the inside of the wire is a circle. This is the cross-sectional area. Or maybe a better metaphor is, imagine you have a sushi roll. Ooh, sushi. I love sushi. Sushi. You cut it into pieces, and the white parts where you can see the rice and all of the toppings inside, that's the cross-sectional area. Cool? Cool. Okay, this is pretty easy. Oh, by the way, keep in mind for the international standard. F is in newtons, of course, and area is in meters squared. Please remember this, very important. Anyways, yeah, let's, I guess, just an example question of this. Hold on, let me erase this. Goodbye, sushi. The sushi. Okay. If you want to try this at home, sure, go ahead. It's not too bad. Imagine we have an object with the cross-sectional area of 4, what's a good number? 4 centimeters squared. And it is given a force of 600 newtons. The question is, what is the stress? Well, this is pretty easy, right? Just plug in the numbers. But here you may notice that this is still in centimeters squared. It has to be in meters squared. Well, how do you convert this? Well, as you may know, I am Indonesian, hello. And the way I learned it for conversion is kucing hitam dalam mobil, desi centil mondar mandir. Okay, this is the kilos. Kucing hitam dalam mobil. This is like the meters, the grams, etc. This is the centimeters. As you can see, it goes up by 2. So we have to divide it by 2. Divided by 2. Oh wait, by 10 to the power of 2. Sorry. By 10 to the power of 2. But keep in mind, there's also a power here. This has to be considered. So this, all of this, gets powered by 2 again. Which basically, we're gonna divide the entire thing with 10 to the power of 4. So basically this will be 4 times 10 to the power of negative 4 meters squared. Amazing! Now just plug in the numbers. This is already newtons, no need for any change. So we know stress is equals to the force divided by the cross-sectional area. The force is 600 newtons, already standard. And the cross-sectional area is 4 times 10 to the power of negative 4. You may know that exponents, when switch aside, I don't know what the official name is, it becomes a negative of it. So you can rewrite this as 600 times 10 to the power of 4. Yeah, the negative changes to a positive, divided by 4. And this is approximately, this is divided by 4, 150. Oh my goodness, what a big number. 150, 0, 0, 0, 0. Oh wow. 1.5 million newtons per meter squared. Don't forget the units. Very important units. Yeah, very simple. Just plug in the numbers and boom, you're done. Let's try some other things. Might be kind of weird, but let's try it. Let me erase this. Just consider this as an intermission. Go get a drink if you want. This is gonna take a while. Oh, by the way, I'm a little bit sick right now, so sorry for bad voice. Okay, this is gonna be a question I just made up. Imagine an object is currently experiencing stress of around, let's say, 600,000 newtons per meter squared. And we know that the cross-sectional area, will be, let's say, 2 meters squared. Now the question is, what is the force applied to the object? Well, again, this is quite easy. We know that stress is equals to force divided by the cross-sectional area. So let's just write that down really quick. Now here, if you multiply both sides by A, we'll multiply this by A, and multiply the left side by A as well to keep it equal. Oh, sorry, let me just add a divider. We can see that A cancels out, which means the force is equals to the stress multiplied by the cross-sectional area. And yeah, just plug in the numbers. This is already standard unit. This is already standard unit. So yeah, just 600,000 times 2, which is 1.2 million. So the object is experiencing 1.2 million newtons of force. Oh my goodness. Very big force indeed. Amazing. Well, yeah, that's it for stress, I think. I don't think there's much more to be told here. Well, I mean, I'm only practicing for my exams, and I'm pretty sure this is enough. Okay, yeah, let's continue. To strain. What is strain? Strain describes the ratio between the length added divided by the original length. You might be wondering, oh, length added, what does that mean? Well, if we remember, this is length added. So elasticity, very cool, right? If you give it a force, it's gonna get longer, or if you push it, it's gonna get shorter. It's gonna get longer by an X amount. And if you remove the force, it's gonna go back to its original shape. Very cool, very cool. Now, the symbol for strain is, oh god, I forgot. This is a moment of learning. I'm gonna Google it really quick. Hold on. Symbol for strain. Epsilon. Okay. Yeah, the symbol for strain is epsilon apparently. What's the unit? There's no unit. Strain is a dimensionless number, meaning that there is no unit. You don't have to write anything. So, yeah, let's just immediately go to a question. Oh, sorry, wait. What is the equation for strain? It's the length added or decreased divided by the original length, with this being the original length and this being the length added. And okay, there you go. Okay, anyway, yeah, so it gets added by this much of units. Yeah, okay, cool. Let's get into practice. Amazing. What's a good question? Oh, okay. Let's say so we have an object with its, I'm gonna write it here, hold on, box, with an original length, its initial length maybe, of 10 meters, very long. But then it experiences strain under a force. We see that the strain is, let's say 0.2. Now the question is, what is the new length? Not what is added, but what is the new length? Okay, let's see. We have the original length and we have the strain. Okay, let's just try to put that into an equation. So strain is equals to the difference in length divided by the original length. We multiply both sides by the original length. The initial length, sorry, we see this cancelled out. So length added or decreased is equals to the original length multiplied by epsilon. And we know that length is 10, epsilon is 0.2. So change in length is 2 meters. Okay, cool. That's cool. Now what? Well, remember, this is the change in length. The changing length, the change in length is basically the length after the force minus the length before the force. Okay, so let's just write that down. LT minus L null is equal to 2. And we know L null is 10. So LT minus 10 is equals to 2. If you add 10 to both sides, we'll get, sorry, let's put this here. LT is equals to 2 plus 10, which is equals to 12 meters. Boom. That's final. Although keep in mind, strain does not have a dimension, so you don't have to do any weird conversions, but you have to stay consistent. If the original length or the initial length is in meters, then everything else has to be in meters, the final length and the change in length. But if the original length is in centimeters, then again, the final length has to be in centimeters and the change in length has to be in centimeters. So you don't have to do any conversions, but just stay consistent, please. Thank you. Okay, let's move on to a different question. I feel like I immediately went to a difficult one. Okay, intermission time. Go grab a glass of water, maybe. I would love a glass of water. I haven't eaten breakfast yet. Really hungry. Should I erase this? Oh, I'm not gonna erase that. Question. Oh, I made a staircase. Oops. Number 2. Let's say, oh, this is an easy one. Yeah, we can do this. Let's say we have an object with its initial length. Oh, why am I writing it there? Hold on. Yeah, it's fine. So its original length of 1.25 meters. But then it experiences force, which changes its length, and the change of length is equals to 5 millimeters. The question is, what is the strain? Remember what I said. We don't have to do any conversions. We just have to stay consistent. This is in meters. This is in millimeters. Oh dear, we're not consistent. So we have to change one of them into the other. I'm gonna change millimeters into meters here. If we remember, kucing hitam dalam mobil, desi centil mondar mandir. Okay? The steps between millimeters and meters is 10. It's 3. And it goes up. So we have to divide this by 10 to the power of 3. This is dividing because the exponent is negative. So this is basically... Oh, so I should erase this. Yeah, after we multiplied it by 10 to the power of negative 3, we change it to meters. Remember conversions. If you're still confused about conversions, maybe practice questions. Maybe I'll make a video about them. I don't know. This is meters. Okay. Question, strain. Okay. We know strain is the ratio between the difference in length and the original length. So yeah, let's just plug in the numbers then. I'm gonna write it here. It feels like there's a lot more space. Is the change in length divided by the original length, or the initial length. Change in length is 5 times 10 to the power of negative 3. The original length is, I'm gonna write this down like this, 125 times 10 to the power of negative 2. Do you know why? Because 1.25 is basically 125 divided by 100, and 100 is basically 10 to the power of 2, and because it's in division, it becomes negative. Okay, so this cancels out, leaving only 1 here, which is 10 to the power of negative 1. This becomes 1, this becomes 25, and we'll get 1 over 250. Or if we want to turn this into a decimal, we can multiply this by 4, which will give us 4 by 1,000, which will give us 0.004. Amazing. Yeah, I think that's it for strain. Yeah, nothing much. Pretty easy, not too bad. Alright, let's move on to the third thing, which is the Young modulus. Wow, we still have a lot of things. I'm already 20 minutes in, goodness. Young modulus. What is Young modulus? It's a coefficient, which is the ratio between stress and strain. Let me write that down. Wait, what's the symbol for Young modulus? A learning moment. Let me Google this really quick. Young modulus symbol. E or Y? Should I use E or Y? I'm gonna use Y because there's gonna be energy later. Yeah, let's say Y. Young modulus is the ratio between stress and strain. Yes, stress divided by strain. Amazing. That's it. It's a coefficient. Yeah. But you might be wondering, oh, what the hell does this do? Well, it helps us find a relationship between the force and the added length. Why? Because if we know the Young modulus, then we know everything else. Let's see. Let's extend this. So we know stress. Do we remember what stress is? Stress is force divided by cross-sectional area divided by strain. Do we remember what strain is? Yes, it is the difference in length divided by the initial length. So here, if we know the Young modulus, and if we know the area and the original length, we can... Wait, what? What am I saying? Oh, sorry. If we know the Young modulus, area, added length, and the original length, we can find the force. Like how much force is applied to the thing. Wow, very cool. Most questions will maybe ask you, oh, what is the Young modulus of this thing? If we know the stress is this and strain is this, blah, 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 blah. Well, yeah. Yeah, basically. Oh, you might be wondering, what's the unit? It's newtons per meter squared. That's the unit. Very weird. Am I wrong? Hold on, this feels very weird. A learning moment. What's the unit of Young modulus? Oh my god, it is newton per meter squared. That's so weird. Okay. Yes, this is the unit. Shall we go to a practice? I think we shall go to a practice. Although I will come back to Young modulus in after slide 4. I think springs. Yeah, Hooke's law, springs. I'll come back because there's something very important here. Anyway, let's say we have a Young modulus. We know the Young modulus is 1 newtons per meter squared. We know the original length is 10 meters. We know that the change of length that it experienced was 2 meters. And we know the cross-sectional area is, let's say, 1 meter squared. Now the question is, what was the force applied? Easy. Let's just plug in the numbers then. So we know y is equals to f over a multiplied by L null divided by the change of length. Let's just put everything in. Y is 1. Force is the one we're looking for. Area is 1. L null is 10. The difference in length is 2. Boom! Okay, let's just do some simple algebra. This becomes 5, and this is divided by 1, so it's basically this one. So 1 is equals to 5 multiplied by f. We divide both sides by 5. That cancels out, so f is equals to 1/5 of a Newton. Amazing! Quite simple. Yeah, just keep in mind that Young modulus allows us to connect between stress and strain, therefore connecting between the change of length and the force applied. Cool. Yeah, I'll come back to this later. In fact, let me just erase this. So when I come back later, it doesn't, I don't have to erase it. Yeah, take a sip of your drink, maybe, I don't know. For Hooke's law. Hey, Hooke's law, right? Yes, Hooke's law. Hooke. I think that's how you spell his name. Hooke's law. Well, before I dive deeper into Hooke's law, I would like to tell you about experiments. In real life experiments, this is how they found Hooke's law. So springs, right? Springs, very cool. Springs, these are springs. Wait. That's how I draw my springs. That's a horrible spring. Hold on. I can draw a better spring than this. I'll make a short spring. Okay. Scientists found out when you give something at the end, maybe like a heavy object of like maybe I don't know 10 kilograms, the length of the spring changes. Ooh. What does this mean? Spring is an elastic object. If we remember here, elasticity is basically something given a force changes shape, and if you remove this weight, it goes back to its original shape. Wow. Oh, what the hell is that line? Yeah, I'm like, oh, it's the same length. Amazing. So that's how they found out about springs. And they were like, let me measure the change of length and then let me graph it. Scientists love graphing. I think, I don't know, I have a lot of homework about graphing. And they found out if they make a graph of force and the change of length, they find that the result is a linear equation. Is this linear? This is linear. Okay, this is linear enough. This is a straight line, by the way. And they saw that, oh, it's a linear equation. What if I find the gradient of this? We know that the gradient is the y divided by x. So f divided by the change of length is equals to the gradient. Let's call it k for now. If we multiply both sides by the change of length, we get f is equals to k multiplied by delta L. This is Hooke's law of elasticity. F, we know, force, newtons, amazing. Change of length, we know, meters. But what is K? K is a constant with the unit of Newton per meter. K basically describes how many force do you need to change the object longer or shorter by 1 meter. So let's say we have K is equals to 10 newtons per meter. That would basically mean you need a force of 10 newtons to give it a length of 1 meter. Hold on, let me draw this. Let's say this is the object with K, and we give it a force of 10 newtons. Basically, it's gonna get added by a meter. This is, let's say this is a meter. This is, I don't know, 1 meter. Okay, amazing. Now you're like, wait a minute. F over delta L. Hold on. Pause. Let me just erase you. Pause. We have F over L here. That means the Young modulus is also equals to the coefficient of spring here. We just saw that. Multiplied by L null divided by A. Amazing. The unit is, oh, what the hell is this? Oh, that's L. Oh my goodness. Sorry. L no. Okay, there you go. Yeah, let's just continue here. Yeah, Hooke's law. That's Hooke's law. Again, Hooke's law is basically how many force do I need to make the object longer by 1 meter? Easy. Example questions? Yeah, sure. Let's say we have. Ooh, wait, I have a really good example question. Shout out to my teacher. Thank you, teacher, for the practice questions. Oh, there's also a lot of practice questions. Maybe I'll try to discuss them here. Maybe that'll be fun. I'm just gonna erase all of this. Intermission. Dun, 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 dun. Oh, this is a really good question. Oh my goodness. Okay. We know that the original length of a spring. I'm just gonna draw it actually. The original length of a spring is 15 centimeters. Oh my goodness. Sorry. This is a wall. Let's say it's a wall. It's connected to a wall, so it's not gonna move. We give it a force, which is equals to half a Newton. And we know that the wait, what is that? Oh, okay. And when we give the force of half Newton, we see that the length changes. What does the length change to? It changes into 27 centimeters. Now here's the question. What will be the length if I give it a force of 0.6 newtons? Wait, oh my goodness, I'm so sorry. I forgot to say that. Keep in mind the coefficient. Remember, F equals K multiplied by X. I'm gonna write that down again. Or delta L in this case. K is always constant. If you have a spring, the K is always constant. It will always be the same. Is it different from other springs? Yes. But is it always the same for one spring? Yes. Okay. If you want to try this at home, ooh, that's so cool. If you want to try this real quick, go ahead. I'll give you, I don't know, a minute or two. This is really awkward. You know what, I'm gonna do it now. Anyway, we see that we have F. Okay, we have F. Do we have delta L? Almost. Okay, let's find delta L real quick. The change in length. Remember, the change in length is equals to the final length minus the original length. The final length is 27 centimeters. Centimeters! Oh no! We have to change it into meters first. How do you change centimeters to meters? You divide it by 100. So this is 0.27 meters. 0.15 meters. Okay, cool. So we know delta L is now 0.27 minus 0.15, which is 0.12. Okay, we have F, we have delta L, we can now find K. F is 0.5. Let's just put that down. Oh, sorry, wait, this is quite ugly. Let me just put the arrow here. Equals to K, we don't know that. Multiply by 0.12. Divide both sides by 0.12, we'll get K is equals to 0.5 divided by 0.12, which is equals to, how much is this? In fact, I think I'm gonna pull up a calculator really quick. Hold on. 0.5 divided by 0.12. Oh goodness. Oh goodness, that's a horrible number. You know what? I think I'm just gonna write this down as so. Yeah, this is K. This is K. Let's just keep that in mind. We have K now. We have K. Okay, now we have K, and we have a new F, and we're trying to find the new L. Okay, let's just write that down. So F, which is now 0.6, multiplied by K, which is always constant for the same spring, multiplied by delta L. This is what we're looking for. Yeah, and then we do some quick things with it. Math. We multiply both sides by 0.12 divided by 0.5. We get 0.6 multiplied by 0.12 divided by 0.5 is equal to the change in length, which is equals to, let me pull up the calculator, 0.12 divided by 0.144 centimeters. Amazing. Wait, centimeters. Sorry. Meters. Yeah, we change everything to meters. It's back to meters now. Pen. Meters. Cool. And now the question is, what is this length? What is this length? Well, remember, the change of length is the final length minus the original length. We know the final length. Oh, sorry, we know the original length and we know the change of length. So, let me erase this really quick. We don't have space to write this down. I'll remove this, I think. Okay. The change of length here, 0.144 meters, is equals to the final length, what we're looking for, minus the original length, 0.15. We add 0.15 to both sides, we'll get LT, the final length, is equal to 0.144 plus 0.15, which is equals to 0.294, yes, meters. Phew, this should be done, but if you want to change it to centimeters, you multiply it by 100 and you'll get 29.4 centimeters. That's the final answer. Woo! Very cool. Very cool. Let's move on to the fifth point. Oh, sorry, let me sneeze. Alhamdulillah. The fifth point is energy. Already? Amazing. Wait, 1, 2, 3, 4, 5. Energy, yes. Energy. Well, we've already learned about energy. Energy, or mechanical energy, with a unit of joule, well, it's basically energy. How much an energy in an object has. Well, we must remember, mechanical energy. This is gonna take a while, sorry. Mechanical energy is conserved. What does conserved mean? Basically means mechanical energy will always be the same for every possible position. Okay? That's cool. Now, what the hell does that mean? Mechanical energy? Huh? What are you trying to tell us here? Well, there's a new type of energy that we will learn. So if we've learned about kinetic energy, half of mass velocity squared. We've learned about potential energy, mass times gravity times height. And remember, in in kinetic energy, there's two types: translational kinetic energy and rotational kinetic energy. Is there also two types for potential energy? Yes. The other type of potential energy is from the springs. Potential energy from springs. EPS. Energy potential spring. What is this equal to? Half. Wait. What is this equal to? Half times k x squared. Oh, sorry, let's not use x here, actually. Let's use delta L. Delta L squared. This is the potential energy for springs. Now, where did we get this equation? Triangles. Triangles. Yeah. 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 It's triangles. That's it. I forgot it's from triangles. Let's go. Anyway. Oh yeah, keep in mind, mechanical energy is conserved. Yes. But if there's friction that's happening, then the energy experiences loss. So it's not conserved. If there's friction. If there's friction. How do you compute? How do you calculate if there's friction? Good question. I don't know. Maybe there'll be a question about it in the exercise. But for now, let's do practice questions. We have an object. Let me draw it for you really quick. Object. This is a wall. This is the floor. This looks really weird. There's a spring. Ooh. Okay. So the block here is going to the spring with a velocity v. It's gonna go to the spring. Let's imagine this. It's gonna go to the spring, and the spring is gonna get squished. Yeah, it's gonna get squished. And then after it gets squished, it's gonna push the block back. It's gonna push it back. Cool? Cool. It's gonna push it back. Now here's the question. If we know the mass of the block is 2 kilograms, the speed is 20 meters per second, the coefficient is 5,000 newtons per meter. The question is, what is the maximum deformity? Wait, the max deformity. Let's see. What is maximum deformity, you might ask? Well, it's basically when the spring is at the most squishiest. When you squish it so much, that just goes back. So remember here, the spring is gonna get squished, the block is gonna stop, and then it's gonna go back. Maximum deformity is when the block stops. Because, well, it's already at its maximum. It's gonna go back then. From that point, right? Yeah. Okay, cool. How do we solve this? I forgot to mention, the floor is frictionless. There's no friction, so mechanical energy is conserved. Okay, let's do that. Let me erase something. What should I erase? Yeah, I think I can still write it here. Mechanical energy 1 will always be the same. Energy 2. Let's look at the mechanical energy 1 before it hits the spring. Well, the block is moving. Okay. So it has kinetic energy. Yeah, that's it. So we have the block's kinetic energy. Then let's look at when it's at its maximum deformity, which is when the block pushes into the spring, the block stops, and it gets pushed back. Remember, the block stops. The block stops moving. What does that mean? There's no more kinetic energy. All of the kinetic energy gets turned into the potential energy of a spring. Yes. So let's just write that down. Half K delta L squared. Okay. We can remove that. mv squared equals to K times delta L squared. I'm gonna keep writing here. What are we looking for again? Alright, maximum deformity. So we have to find the change of length. Change of length will be equal to maximum deformity in this case. If we divide both sides by K, we'll get that mass velocity squared divided by K is equals to change of length. And there's a power here, power of 2, so we have to root it. So, oh, I should not be using this in arrow. Be the square root of mass times velocity squared divided by K. There's no more space to write. I'm gonna I'm gonna erase something. Hold on. Let me erase something. I'll erase. Maybe I'll erase this. Yeah, we have mass, we have velocity, we have K. Let's just plug that in. Where's the pen? Give me the pen. Thank you. Maximum deformity is equals to mass 2. Oh yeah, V here, we can just put it outside because it cancels out. The force, V multiplied by mass divided by K. So we have V 20 divided by 2, 5,000. This becomes 2,500, which is equal to, the square root of that is equals to 50. We can cross the 0 out, so we'll get 2 over 5 meters. This is the maximum deformity. Amazing. This question may be extended to like, oh, what's the potential energy at half of it, half of the maximum deformity? But at that point you can just, oh, okay, just divide the maximum deformity by 2 and then find the potential energy with that. Easy. Okay, let's move on to the 7th point. Wait, 6, 7, 1, 2, oh, 6, 7, damn. Oh, sorry, the 7th point, spring formations. Oh, I thought it was the 6th. 7. Spring form 7. 6. Spring formations. I should do more research because I forgot the English words for this. I may just say this in Indonesian. Well, there's 2 types of spring formations. Let me just draw. These are walls, by the way. There's parallel, which is built like this, where you have 2 springs attached parallel to each other. And we have, I think, series. I think that's the English word because it's like a series of circuits. I don't know. Oh shoot. This is 2 springs, by the way. It's divided by that part. This is spring 1 with a constant of 1. Spring 2 constant of 2. Spring 1 constant of 1. Spring 2 constant of 2. Now you might be wondering, okay, this is a little bit complex. How do I calculate the coefficient of the system? Well, it's quite easy actually. For parallel systems, the coefficient of the system is basically equal to the sum of all of the springs. Easy. Now you might be wondering, where did you get this from? Should I explain it? I think I'm gonna explain it. Okay, so we know that if the object here gets displaced by, oh wait, I should maybe write this somewhere else. Yeah, I'll just write this here. Well, I'll erase this. If the this object gets displaced by, let's say x, automatically the two other springs gets displaced by x as well. Correct? Correct. Of course. Simple math. This goes down by 2. This also goes down by 2. Oh, gets longer by 2. Sorry. Gets longer by 2. So we see that the x is same for every case. Okay, let's look at Hooke's law again. F is equals to k times x. Alright, cool. So, we see that x is constant. Okay, that's cool. No problem. Which means that, oh dear, I may be forgetting. A moment of learning for all of us. What was I trying to do? Um, hold on. It's a moment of learning. Whoa! Where did we get this from? Oh, okay. I understand it now. Amazing. A moment of learning. I'm so ready for the test. Hopefully. I forgot to mention here in Hooke's law. If you have a spring, and you pull it with a force, let's say F, it's gonna pull back with another force. What is this force? This is basically Hooke's law. This is Hooke's law. This is Hooke's law. Oh shoot, wait, what the hell? What? That's not a good circle. Yeah, this is Hooke's law. This is Hooke's law. If you pull it by F, it's gonna come back as Hooke's law again. It's gonna pull back. It's gonna pull back. If you pull a spring, it's gonna pull you back. The pullback is the Hooke's law. Okay, so imagine we pull this by F. This is gonna pull back by F1. This is gonna pull back by F2. If we look at dynamics, we see that F is equals to F1 plus F2. Remember dynamics? Maybe I'll make a video about that, maybe not. Let's see. So F, we see it's K times X. F1 is K1 times X1. And F2 is K2 times X2. But remember, I said the displacement is always the same. So we can actually divide everything by X, so the X gets disappeared. So the final system would be like this. So the system of springs, the coefficient of the system is equals to the sum of all of the coefficients. Amazing. Series. How do we get this? Let's see. Well, we know that all of the forces here, all forces will be the same. It will be the same. Why? I don't know. Ask my physics teacher. Maybe I'll ask him or her or they then. I'm not telling you, because random people might find this video. Hello. Yeah, all forces are the same. Yes, okay. All forces are the same. Yes, all forces are the same. And if this gets displaced by X, X will be equal to how much this gets longer by plus how much this gets longer by. Yes? Okay, let's write that down. X is equals to x1 plus x2. What's x? X is f over k. Okay, that's cool. F over k is equals to f over k1 plus f over k2. F is always the same. Okay, let's just goodbye. So we'll get 1 over k is equals to 1 over k1 plus 1 over k2. Boom! So 1 over the system is equals to 1 over the first one plus 1 over the second one. It's very similar to this, but this one is 1 over the thing, and this is just the thing over 1, I guess. Yeah, that's cool. Practice questions. I'm gonna erase all of this. This is a moment of intermission. Wow, this is... Apparently, I'm looking at the recorder right now. Apparently, it's been going on for almost an hour. Doesn't feel like an hour. Feels like 10 minutes. Oh boy, that's amazing. Imagine my mic has been off the entire time. Oh my god, that would be depressing. Like that one, I think Singaporean teacher. It's been talking for a few hours. Like damn, that's devastating. I hope the mic is on. I think the mic is on. Hopefully the mic is on. Anyway. Practice. Look at this. Oh wait, I need to make this longer. Ooh, scary. That's a wall. So the spring doesn't move. We have a formation like this. Spring 1. Spring 2. Spring 3 gets combined into a system, then gets added to spring 1 and spring 2. There's like an object here. The question is, what is the coefficient of springs of this system? Oh my god, how do you do this? Well, let's just split the work first. I would advise you to do the parallel ones first, and then do the series one. So yeah, let's do the parallel one first. Okay, let's say this is K1, this is K2, this is K3, this is K4, this is K5. K1 is equals to K2 is equals to K3, which is 200, I think. Yeah, 200 newtons per meter. K4 is equals to K5, which is equals to 300 newtons per meter. Question is coefficient of the system. What? Okay, this is how I would do it. I would find the coefficient of system here first, and then once I find that, I will describe it as one spring. That one spring will be connected into 3 other springs. Okay, so let's find this first. The first system, let's KS1, be equal to K1 plus K2 plus K3. Remember, this is a parallel. Oh wait, I deleted it. Damn. Say K1 plus K2 plus K3. We know that K1 is equals to K2, which is equals to K3, which is 200. Which is basically 200 multiplied by 3. And we'll get the first one is equals to 600 newtons per meter. Amazing. Now we have this, the first system. What the hell does this mean? This means that we can actually ignore all the 3 springs because we already calculated it and symbolize it as just one spring. What's the coefficient? This is the coefficient. This is KS1. Are you allowed to draw this in the exam? I don't know. I don't think so. But yeah, just keep this in mind. Keep this in mind. This is basically the same thing. So, okay, this is series. We know. Okay, that's easy. 1 over k. Yes, the entire system is equal to, where do I write it equal to? There's no room here. I'll just write this here. 1 over ks1 plus 1 over k4 plus 1 over k5, which is 1 over 600 plus 1 over 300 plus 1 over 300. Okay, which is 5 over 600, I think. Yeah, 5 over 600. This becomes 1. This becomes 120, I think. Yeah, 120. Boom. But this is 1 over the system. Okay, so we have to turn it around, and we'll get the system, the coefficient of strength, is equals to 100 newtons per meter. That is the final answer, ladies and gentlemen. Amazing. Are we done here? We are done here. That is all of the material. Hopefully, I did not forget anything. Now, a problem. There's a lot of problems. Exercises, maybe. Should I do all of them? How many numbers is this? A lot of numbers. Okay, let's just speed run through this very quickly, very quickly. Okay, let's see. The first number. We have a graph. Ooh, graph? Did I delete it? I deleted it. Damn. Okay. Yeah? We have a graph. Alright. Graph of force and displacement. Constant line. We see at this point this is equal to 0.05. Oh, this is meters, by the way. Meters. Newtons. That is 50. Okay, question is, what is the coefficient of spring? Okay, easy. We remember that K is basically the gradient of the graph. In this case, it's 50 over 5 times 100. Okay, 5 times, why is it 5 times 100? Okay, 0.05, basically 5 over 100, and if you divide that as a, if you use that as a divisibility, it gets upside down. So 5's at down and 100's at top. Yeah, I don't know, I'm hungry, which is basically 10 times 100, which is 1,000. Okay, cool, that's number 1. Amazing. Oh my god, my handwriting is so messy. Let's look at number 2. Mass 200, gravity taken as 10. Okay, this isn't too bad. Number 2, we have a rod with its wait, what? Oh, with the cross-sectional area. Yeah, I'll write it later. It gets added with a weight. Here, length gets added. This is L, delta L. I hope you can read that. That's delta L. So we know that delta L is equals to 1 millimeter. Mass of the object, this object, 200 kilograms. We take GS10, thank god. This is easier for mental maths. And the cross-sectional area is equals to 0.5 centimeter squared. Oh my goodness! Oh, and the original length is equals to 4 meters. Oh my goodness. Okay, we have to convert all of this first. This becomes 10 kucing hitam dalam mobil negative 3 meters. This becomes 0.5 times 10 to the power of negative 4 meters squared, or 5 times 10 to the power of negative 5 meters squared. Okay, cool. Now the question is the stress, the strain, and the modulus, the Young modulus. Okay, easy. That's easy. Okay, let's start now. Sigma stress F. Do we have F? Yes, we do. This is F. Let's pulling it down. F here is weight, and we know that weight is mass times gravity. So we know F will be 2000. Okay, you might be wondering, what? Why is F weight? Well, let's remember in dynamics, we have weight, normal force, friction, and tension. Weight is one of them. This is weight. It has a mass, and it's getting pulled down by gravity. Therefore, the force here is weight. And the weight is causing the rod to extend by 1 millimeter. So the force here will be the weight, which is equals to 2000. And the cross-sectional area is here, 5, and the exponent goes up. Holy moly, this is a big number. 4 and 4 0 0 1 2 3 4 5 40 million. Okay, that's cool. Seems like a legit number. Okay, that's 1. Now we'll find the strain. Length added is 10 to the power of negative 3 divided by the original length, which will get 1 over 4000. Okay, and Young modulus is equals to stress. 40 million, bro. 40 million divided by strain. Oh my goodness. What is this number? Multiply divided by 1 over 4000. Holy, what is this number? The Young modulus is 16 0 0 0 0 0. Wait. 1 2 3 4 5 6 7. 1 2 3 4 5 6 7. 1 2 3. This is the Young modulus? 160 billion. Teacher, what is this? Hell no. Okay, number 3. Oh, it's... Oh, okay. It's basically more. Okay, okay. Loki, I'm gonna be really honest with you guys. I'm so lazy to do this. I'm gonna do the easy ones instead. Oh, let's do number 8. Spring formations. K1, K2, K3. Okay, cool. 2 springs of K and 2K. Wait, what is this question? What the hell? I have no idea what the question is trying to make me do. So there's 2 springs with the constant of K and 2K. Put it to a series and then put a weight of 2m. And then next. Oh, what is this then? Okay, you know what? This is wrong. I think this is wrong. So first we need to find the series of K and 2K. And then all of that gets put into a parallel one and then given a weight of 4m. And then we need to find a ratio of the difference in length for the series and the parallel. Oh my goodness me. Okay. Okay. You know what? Let's just say this is 2K. All of this. This is K. Cool. Cool. Anyway. So we know the system, 1 over the system. Remember. 1 1 over k plus 1 over 2k, which is 3 over 2k. So ks is equals to 2k divided by 3. This is for series. This series 1. The parallel one is basically the sum, which is 2k plus k, 3k. Parallel. Okay. Oh my god. I can do this. I can do this. And then the question is, oh, this is given a weight of 2m. This is given a weight of 4m. Oh my goodness. Okay. Let's find the difference of length first. So we know f here would be 20 is equals to the constant multiplied by the extended. So difference in length would be force. Let's take gravity as 10. 2k and 3 goes up. It's basically 30 over k. This is for series, and parallel it's 4m. So it will be 40 divided by 3k. And we need to find the ratio between these two. So 30 over k divided by 40 over 3k. We can cross this. So the ratio is 9 to 4. Oh, it's E. Amazing! I did it! Yeah, I think I'm on the verge of not wanting to do this anymore. So yeah. Sorry. Let's recap really quick. Elasticity is basically something, if you give it a force, it's going to change its length, and if you remove the force, it's going to come back. In elasticity, there's stress. Stress is basically the force over the cross-sectional area with units of newtons per meter squared. Strain. Strain is basically the ratio between the difference of length divided by the original length. It has no unit. Young modulus is the ratio between the stress and the strain. Easy. Hooke's law. Hooke's law states that K, imagine we have a K, and we will need an F amount of force to make the spring with a constant of K move by 1 meter. Okay, cool. Energy. We learned a new thing in energy, which is the potential energy in springs, which is half multiplied by K multiplied by delta L squared. Delta L will be the difference in length. Yes, okay. Spring formations. We have series and parallel. Series. These are series. And oh no, I removed it. Yeah, series is 1 over ks is equals to 1 over k1 plus 1 over k2, and parallel is ks is equals to k1 plus k2. And here's the example questions. I only did 3 because I'm really tired and hungry. Yeah, thank you so much for watching. I hope this video is helpful for anyone who's watching this. It's definitely helpful for me. I learned a lot of new things. And yeah, sorry if there's any mistakes. And if you have an idea on what I should make next, feel free to tell me. Okay, thank you for watching.